Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. Ant. In this tutorial video, we'll go through this AQA topical question. This is specifically on redox changes, redox chemistry. So in this question, chlorine is an important industrial chemical. We know that chlorine comes out as an element in this diatomic molecular form, where you have chlorine, which is 287 electronic configuration from your IGCSE chemistry. Therefore, we will have 7 electrons in the outer shell, which of course is not going to be happy on its own, which is why it form a covalent bond with another chlorine atom, such that you have 2 atoms that are bonded covalently to give you a molecule, hence you call it a diatomic molecule. In this equation, we use this MnO4-, which come from KMnO4 reacting with chloride from the hydrochloric acid to give us the chlorine there. Deduce the half equations. The half equation meaning we need to show it with electrons. Oxidation in terms of electrons come from this part of the acronym. It's oil rig in full. We're looking at oil there, which is basically oxidation is loss of electrons there. So we have Cl minus becoming Cl2. So we need to balance the atom first of all. So 2 Cl minus. And we need to add electrons on the right hand side. As we could see that there is a -1 times 2. There is a -2 on the left. This one has 0 charge as a molecule. I need 2 of the electrons to give me -1 times 2, which is -2 on the right hand side as well. The next part is oxidation state. Calculating oxidation state, oxidation number is very, very important. The oxidation number of an ion follows the charge of the ion. So -1 is the sum of the individual oxidation number. I have 4 oxygen. Oxygen is always -2 in a compound, except when it's an element, then it will have 0 oxidation number. Here it is bonded to something else. Here's a -2 oxidation number. Find out the manganese oxidation number, -1 plus 8. Each manganese is +7 there, so it's called potassium manganate 7. So the full name there would be potassium manganate, and then VII, as you're supposed to know to use Roman numeral to represent the oxidation number of the transition metal in their compounds there. Now deduce the half equation for the reduction of that in acidified solution. So you need the H plus there to form the Mn2 plus and water. So the MnO4- in the presence of acid is going to be reduction. So the oil rig part of the acronym, as I mentioned earlier, this is reduction is gain of electrons. So we're going to add in electrons on the left hand side. As you gain the electrons, you're going to form Mn2 plus manganese 2 ions, as well as water plus water there. So I think we have gotten everything we need. We just need to balance the equation in terms of atoms. First of all, balance the atoms. 1 manganese, 4 oxygen. Here you've got 1 oxygen, so put in 4 on the right hand side. Now 8 hydrogen atoms on the right. You must have 8 hydrogen atoms on the left. Last but not least, all the atoms are balanced now. So your job really now is balancing the charges. The molecule has no charge, so 0 charge there, +2 from one of the Mn2 plus. So you need a +2 overall on the right. We have a -1 plus 8 is +7. So you need to go from +7 to +2. You need a 5 electrons there. So that is the balanced half equation. In part B, chlorine behaves as an oxidizing agent. So write the simplest ionic, the simplest, that means the simplest whole number ratio ionic equation for the reaction of chlorine there, which is Cl2, with the bromide, which is Br-. So the Cl2 plus Br- is going to give us the classic IGCSE reactivity, which is forming the Br2, where the chlorine kicks out the Br2 from Br- in a displacement reaction and becomes Cl-. But you need to balance the atom. There are 2 Br, so 2 Br-. There are 2 Cl, so 2 Cl-. Balance the atom to chlorine, to chlorine, to Br, and 2 Br. Balance the charges, 0 charge for the molecule. -1 times 2 is -2. -2 over on the left. -1 times 2 is -2. Molecule has no charge. -2 on the left, -2 on the right. Everything is balanced. Now give one observation that will be made, or they will be observed. So halogens are colored. So you need to know the colors of the halogen. meaning to say the element CO2 and Br2 are colored. As we produce the Br2 element, we will see a red-brown liquid will form. And they say give one observation, they don't say give the observation. We could also see that the pale green color of the chlorine gas, the pale green color, especially if we use the gas itself, the element itself, fades. That means it gets lighter as it reacts. They just need one observation, so really it could be or either of each observation, to be honest, because it's just asking for one. Now, in terms of electrons, state the meaning of the term oxidizing agent. I usually ask students to define oxidizing agent generally first. So oxidizing agent oxidizes the other substance. So we write down what we normally write first, oxidizes the other substance. And what happened to itself? It must be getting reduced, and itself get reduced. After we think about what happened to itself, we can think about the definition of reduction as part of oil rig, where reduction means gain of electrons. So if itself get reduced, so therefore itself gains electrons. Rather than remembering stuff unnecessarily, why don't we just try and remember our general definition, and from there we can try and relate reduction to gaining of electrons there. Part C, chlorines can oxidize water slowly to form oxygen. Write equation for this reaction. Let's see, chlorine reacts with water to give you oxygen. This is O2. What is left behind then? That must be HClO, I think, or is it HCl? Give us in the chlorine containing species that is formed. So let me try and balance this equation. I wonder if it is HCl or HClO. I think it's HCl because you can balance the equation like that. As you could see that there is one oxygen there. So this gives you half O2 because there's one oxygen atoms there and one oxygen atom. Cannot change the identity of oxygen molecule, diatomic molecule from your IGCSE syllabus. But we got two hydrogen and two chlorine atoms, therefore two HCl. Oxidation state of chlorine in the species form. So we're looking at just one of these HCl. The hydrogen is +1, the overall is 0. So +1 plus Cl equal to 0. Cl equal to 0 minus 1. Cl is -1 there. So it's just -1. Part D, this is about structure and bonding. This is about chlorine having lower boiling point. So what we say lower boiling point means more volatile, easier to boil. We're going to talk about structure and bonding. So both the chlorine and bromine have simple covalent structure. If you have simple covalent structure, simple molecular structure, we are just breaking the weak intermolecular forces between the molecules. So therefore, boiling it or boiling them just breaks the weak van der Waals forces. We can also call it induced dipoles or London dispersion forces. Whichever word you like, they all mean the same thing. London dispersion forces. Should probably write it on the new line, I guess. London dispersion forces, temporary dipole, induced dipoles. All of these means the same thing. These are between the molecules. These are weak forces of attraction. Really what we are trying to do here is think about the strength of van der Waals. So down group 17, we know that Br2 has greater number of electrons, greater total number of electrons in the molecule. Not only that, that is the first thing that's going to result in stronger van der Waals. And also, we talk about surface area. Br2 molecule has greater surface area than the CO2 molecule. So overall, what we can establish there really is that therefore stronger van der Waals, stronger induced dipoles, stronger temporary dipoles between Br2 than between Cl2 therefore requires more energy to break. And if you require more energy to break, your boiling point is going to be a little bit higher for the bromine. In this question number 2, so vanadium is an important metal. This is an alloy of iron and vanadium. So we have some standard enthalpy of formation data. Remember that when we have enthalpy of formation data, usually they ask us to calculate something. So what we are supposed to do is use data in the table to calculate standard enthalpy change for this reaction. This is element. When you have element and you also have vanadium as an element, we know that enthalpy of formation of element is going to be 0 because you are forming the element from the element in its standard state under standard condition. That doesn't make sense there. Number 2, state the type of reaction that it has undergone. And number 3, suggest one major reason, blah, blah, blah. So let's do this question part by part, but whatever you do, make sure you do number them so that you do answer each and every part of the question. So if we have reactants going to product and we have enthalpy of formation, so we involve the elements, which is going to go upward like this and upward like that. So that is the formation of the product, and I do have the formation of the reactant somewhere nearby there, the formation of the reactant. So therefore, we can see that Hess's law says that enthalpy change of a reaction doesn't matter which pathway you take, whether you take the direct pathway or the indirect pathway, where we're going to go down, therefore minus the enthalpy formation of reactant plus the enthalpy formation of products there. So enthalpy change of reaction is going to be the sum, or if I use the other word, so this is the total enthalpy of formation of the products minus the total enthalpy of formation of the reactants to work out the enthalpy change of reaction here. So we have 5 mole of the calcium oxide. Because this is kilojoule per mole, this is for forming 1 mole of the substance from its elements in standard state under standard conditions. So minus 635 there for the calcium oxide, multiplied by 5, that's for the product side. And for the reactant side, I have 1 of the V2O5, that is minus 1560. And just pressing that onto the calculator. So 5 times 635 negative minus 1560 negative. So be very careful with the double negative there. Always use bracket, sign, value, and unit for the enthalpy change there. In terms of the type of reactions, as you could see, the V2O5 loses the oxygen to the calcium steals away all the oxygen from the V2O5, leaving behind the element V, and therefore the calcium gains all the oxygen. So this implies that calcium is a more reactive metal than vanadium. So therefore, you know, it can displace vanadium from the oxide of vanadium. So this is about reactivity of metals in terms of the redox displacement. So it's a redox displacement. I think in IGCSE you call it displacement, but then it's essentially a redox reaction where a more reactive metal displaces the less reactive metal there. In terms of number 3, suggest one major reason other than the cost of heating. Why this metal extracting is expensive. Why is it expensive? Oh, at a high temperature, but that one is expensive, so we already established that it's expensive. So other than the cost of heating, let me think. Suggest one major reason why this metal is expensive other than the cost of heating. I guess we can also think about, you know, we are wasting precious element in order to extract this V2O5. So it could be that, you know, it says suggest one major reason. So not the energy cost in terms of high temperature. I'm thinking that, you know, we are wasting precious calcium metal, which could be used for something else. So perhaps it could be one of the reasons. So this process uses another metal, which is calcium, that might be useful, or that might be more useful or valuable for other purposes or for other users. because, well, that's what come to mind. But if you have other sensible explanations, I'm sure it's alright for a suggestive kind of question there. In part B, so we have these ferrovanadium alloys produced by reacting aluminium with a mixture of V2O5 and iron 3 oxide. So we just have aluminium with iron 3 oxide here. We know about the reactivity series, POSOCA, Ma, and then Zil, Z, and then I, and then L, and then hydrogen. As you have these less reactive metal below hydrogen, there will be the copper, silver, and gold. These are straight from IGCSE chemistry. And what we have is aluminium is a more reactive metal than irons. Therefore, aluminium reacting with Fe2O3. The aluminium is going to take away all the oxygen, leaving behind the iron. Therefore, I need to balance my equation. So 2 aluminium atoms there. Therefore, I got 2 aluminium atoms on the left, 2 iron atoms on the left, so 2 iron atoms on the right. Writing equation, part 1 is done. State the change in oxidation number. Part 2 is not done yet. This is element, so the aluminium is 0. And this is in a compound, so the aluminium is plus 3, because this is basically Al3 plus 2 of them. And then 3 of the O2 minus. You can see the charges cancel out. Plus 6 cancel out, minus 6. Al2O3 is an ionic compound. Ionic compound has no overall charge, even though they're made out of oppositely charged ions there. So therefore, the change in oxidation number is going to be final oxidation number minus the initial oxidation number. The change is increase of 3, or you can say plus 3 there. In part C, pure vanadium for nuclear reactors is formed by reacting hydrogen with purified VCO2. So we have the other product is HCl, write an equation. So hydrogen gas, because there's H2 there, plus VCO2. We're going to get vanadium pure metal, and we're going to get HCl and 2 HCl in order to balance the equations as the only other product there. Now identify 2 hazards in this process other than the fact that it operates at high temperature, so we don't need to talk about that anymore. Hazards, so what can we talk about? Number 1, HCl is a toxic gas, it's a corrosive gas, it's a toxic gas, so somewhere along that line should be alright. And what else? Hazards. I guess using H2 to react requires high pressure, and of course we know that hydrogen is flammable. Hydrogen is highly flammable gas, so very explosive if it reacts violently. So that could be another safety hazard there. Now, deduce why this process produces pure vanadium other than the fact that purified VCl2 is used. Well, because this will come off as a gas, so the reaction can get rid of the HCl as a gas, and if we use excess H2 gas, then all of the VCl2 reacted, and any excess H2 gas can just be vaporized away. So as you just allow it to escape, you don't need to separate out the reactants from this reactant which is completely reacted. This is going to be a solid metal, and you don't need to separate the solid metal from the gas, because you can just let the excess H2 to just escape, to be honest. And that's it overall for that 11 marks question there. In this question number 3, what we have is swimming pool kind of chemistry. We treat it with chlorine gas, which is this diatomic molecule here. When chlorine reacts with water, the chlorine is both oxidized and also reduced. And this is a classic reaction called disproportionation. Disproportionation is a special redox reaction where one species is both oxidized and reduced. And this topic here, equilibrium, that means we're going to show using the term or the sign reversible changes. Write an equation, classic case study, CO2 plus H2O. you get two chlorine containing species. The first one is this chlorine -1 oxidation number. The second one is this chlorine +1 oxidation number. I say it's a case study. This is chlorine 0 in this element, and write the oxidation state of chlorine below the species. This is typically how I write my oxidation numbers with the symbol of the atom that it represents, because oxidation number is for a specific atom rather than for a molecule, and therefore I write it only for a certain atom with the number stated in bracket. If you don't write out the bracket, I'm sure it's pretty self-explanatory. Now this is element. If it is element, the oxidation number is 0 on its own. Here you have hydrogen +1, so therefore +1 plus Cl equal to 0 overall, as the compound is uncharged, so move the +1 to the other side, therefore it's chlorine -1. Whereas for this HClO, is a pretty important species. It has got bleaching property, and this is what is present in your bleach, in your house bleach, which smells a bit like chlorine, because chlorine water does give you this thing which has bleaching property, whereas this is not bleaching. The bleaching agent in fact is the HClO here. So +1 for the hydrogen. So what we get is +1 plus chlorine plus -2 for each oxygen compound. Chlorine is +2 -1, chlorine is +1 there. In part B, the pool manager maintains the water at a pH slightly greater than 7.0. So this would mean this is slightly alkaline condition, slightly more OH- than H+. So with more OH- ions at a pH greater than 7, therefore this will neutralize. That means they will react with the H+ from Cl2 in water. Earlier we produced Cl2 plus H2O, giving us the HCl plus HClO. So what we are saying is, the HCl can get neutralized, the HClO can get neutralized. So both the HCl and HClO gets neutralized. So what happens as both of them get neutralized? How does this affect the equilibrium when chlorine is added to the water? So therefore the equilibrium refers to the Cl2 dissociating in water. It will shift to the right hand side to produce more H+, i.e. more HCl, more HClO. In part C, why in the world is the chlorine used even though it is toxic? So chlorine and bromine are toxic substances, but why in the world do we put into swimming pools? There are 2 marks to this question, so we need to write in 2 points. So sometimes we use things even though they are toxic because they have far greater benefit, and in terms of your swimming pool water, you do need it to be clean of bacteria and whatnot. We only use in small enough quantity, only use in regulated small amount that is safe enough, not like it is toxic, but it's not extremely toxic in a regulated small amount, such that it would be lethal. It wouldn't really kill you even though it's toxic. But of course, the second reason being that what I mentioned earlier, the health benefit compared to not having clean water in the swimming pool, the health benefits that cleaner swimming pools provide far outweigh. So basically it far overcome any adverse effect, any adverse or harmful effect that it might cause. But then obviously these are regulated heavily by the pool operators, by the government as well, such that there wouldn't be little in the amount that they're actually using. And that's it for that overall 6 marks question here. Just last part to this question in this tutorial, which of these species is the best reducing agent? So we know reducing agent is going to reduce other substances, and that will mean what happened to itself. Do not forget that the definition is not complete until you say what happened to itself. Itself gets oxidized. So we are not really referring to the halogens, because the halogens, the X2 halogens, are good oxidizing agent. They are not good reducing agent. So that is a fact there, where they do like to gain electrons, where they do like to get reduced, and therefore they are acting as oxidizing agent. So A and C is definitely out. So in terms of oxidizing ability, we know that the chlorine is a better oxidizing agent than bromine, than iodine. Whereas in terms of the reducing ability, we have to go the other way around, where the iodide is going to be the best reducing agent out of the lot, compared to the Br minus, compared to the Cl minus. This makes the I minus a very good reducing agent. Example, we use Ki aqueous as a good reducing agent ever since your IGCSE and even now in your A-level curriculum. I think that's it really. I'll leave it there for these particular tutorials on redox changes. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. And do follow me at ptet.chemistry. That's at ptet.chemistry to support my work on Facebook, Instagram, Twitter, and Telegram to get connected. And don't forget to get in touch if you need help with one-on-ones or in a small group private tutorial. I'll see you in the next lecture tutorials as well as question tutorial. Thank you for watching again.